In this video, we consider hemiacetal formation under acidic conditions. So recall from our previous discussion that there are two options for promoting a reaction between aldehydes or ketones and alcohols. You could make the nucleophile more nucleophilic by deprotonating it. That was option one. Option two is to make the carbonyl group a better electrophile. And we do this by protonating it with acid. Okay, so let's look at the mechanism of this process. So step one will be protonation of the carbonyl oxygen with strong acid to give the protonated carbonyl. So note that you have seen a structure that looks like this protonated carbonyl before. It's simply the second resonance structure for the oxocarbocation we looked at during the SN1 mechanism. So the oxocarbocation resonance structure with the protonated carbonyl is depicted in this figure. So once you have a protonated carbonyl and something that has a carbocation as a resonance structure, you know that it is electrophilic enough to react with any old nucleophile, including a neutral nucleophile, including a neutral alcohol as a nucleophile. So then step two will be nucleophilic attack of the neutral alcohol on the protonated carbonyl. Like in all cases where you have a neutral alcohol as a nucleophile, you end up with a positive charge on the alcohol-oxygen atom in the intermediate. There is now no longer a positive charge on the oxygen that originally started out life as the carbonyl oxygen. We have taken the electrons in the CO pi bond, we have pushed them onto this oxygen to get rid of the positive charge, and it ends up neutral overall. Step three now is proton transfer to the solvent. In this case, under basic conditions, we had proton transfer from the solvent. Now, under acidic conditions, we have proton transfer to the solvent, CH3OH, methanol in this case, to give the neutral hemiacetal product. Okay, so note that steps 2 and 3 of this mechanism are very similar to steps 2 and 3 of an SN1 mechanism with a neutral nucleophile. We have the nucleophile attack, and then we have proton transfer to the solvent. Now, this is a really important point. That's why it's in red. The base in the final step is methanol, CH3OH. Yes, it's a weak base, but it is the strongest base that can be present under acidic conditions. You cannot have CH3O- present under acidic conditions because before it could do anything else, it will react with the acid and make CH3OH. Therefore, CH3OH is the strongest base that is present in the reaction flask. So, we have now seen that hemiacetal formation can take place under either basic or acidic conditions. We first looked at the basic mechanism, and the overall reaction under basic conditions is you have your carbonyl compound, you're reacting it with NaOCH3, sodium methoxide, in methanol as the solvent to get the hemiacetal. And remember that only a catalytic amount of base was required for this reaction because it is regenerated in the last step. Under acidic conditions, same starting material, same solvent, but instead of a catalytic amount of base, we now would add a catalytic amount of strong acid. And looking back at the mechanism on the last slide, that acid is also regenerated during the last step of the mechanism. Now, as we will see in the next video, under acidic conditions, the reaction does not stop there. The hemiacetal is inherently unstable to acidic conditions, and as we will see, it will actually react further to make an acetal.